Here are the notes for section 8.5, applications from science and stats. So work, just a reminder, work is equal to force times distance. So the force you apply times the distance it moves through. So example 1, find the work done by the force F of x equals cosine pi x newtons along the x-axis from 0 to, half meter. So since our force is variable, I have to use an integral. So I'm going to start at 0, move it to 1/2. And then my work force function is cosine of pi x. And I just need to evaluate this. So this is going to be sine of pi x, 1 over pi out front, evaluated from 0 to 1/2. Or let the calculator handle it. So that's going to come out to be all in about 0.318 Newton meters. Okay, so example 2. So a leaky bucket weighs 22 newtons empty, is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 Newton meters. The bucket starts with 70 newtons of water, but leaks at a constant rate, just finishes draining as a bucket reaches the top. So the top of the bucket's empty, the bottom bucket's full. Find the amount of work done lifting the bucket alone. Well, the bucket alone is relatively straightforward. It has a constant weight, work. So the force required is the weight of the bucket. You're lifting it 20 meters up, so the work just lifting the bucket is 440 Newton meters, or actually the unit would be joules. Lifting the water alone. Okay, so let's see here. Let's see. So we start with 70, and it's going to be empty. Actually here. So the water's draining, so we need to find out the force, the weight. It's not actually going to be 70 newtons the entire time because it's empty at the top. So the force, or the weight of the water, let's see here. So we know that it is on the ground, it weighs 70. You know that 20 meters up, it weighs 0. So the slope here is negative 70 over 20, or negative 7/2. So that's how fast it's draining out. So that means the weight of the water is going to be is 70 minus 7/2 x. That'll make it empty. When it hits 20, this will turn into 0, which means that I need to do, though, since my weight is variable, the force I'm applying changes. So 0 to 20 of my equation. So lifting the bucket alone, the water alone, 70 minus, we'll make that 3.5x from 0 to 20, takes 700 joules of energy. Lifting the rope alone. Okay, so the rope weighs 0.4 newtons per meter. So the weight of the rope is 0.4 times 20 minus x. When x is 0, when I've lifted it nothing, it's the full weight, or 8 newtons. So from 0 to 20, 0.4 times 20 minus x dx. Because as there's less rope, it's going to get easier to lift. So this is going to be 0.4, 20 minus x from 0 to 20. So to lift the rope alone, it takes 80 joules of energy. So lifting it all together, the bucket, plus the water, plus the rope, 440 plus 7, takes a total of 1,220 joules to lift the rope and the water and the bucket, if the bucket drains. So these two you have to do integrals on, because the force, the weight of the object you're trying to lift is changing. The bucket's full at the bottom and empty at the top, so it gets lighter as it goes. Same thing happens for the rope. You have to pull the full weight of the rope at the start, but as it gets up to the top, the rope should have no weight, there's just no rope left. Okay, so example 3 says a conical tank shown to the right is filled to within 2 feet of the top of the tank with olive oil weighing 57 pounds per cubic foot. How much work does it take to pump oil to the rim of the tank? Okay, so let's see here. So so there's so that distance is half y. So this edge here is y equals 2x, or half y, which is why down here this says the radius is half y. So this tank looks like it appears to be 10 feet deep in total. The oil is currently sitting at the 8-foot mark. So how much work does it take to finish filling it? So let's see here. Force required to lift this slab is equal to the weight. Okay. So that's our density. So the weight of the olive oil is going to equal 57 times its volume. But the problem is the volume is changing because these discs are getting larger and larger and larger. So the volume is going to be, so we're going to assume that like there's discs, cylinders, so pi r squared h. So that's the same thing. If you look at your picture, r is half y. H is the same thing as delta y. It's the change in height of my disk. So this is pi over 4y squared delta y times 57. So this is the weight of lifting the olive oil. So let's see here. So that's the force. The distance I have to lift it is 10 minus y. So I'm starting here up to here. So my force equation is the weight, 57 pi over 4 y squared delta y. The distance is 10 minus y. So let's see here. How much work is done to take to the rim of the tank? Okay. Oh, no, I'm sorry. Picture's long. The tank is 8 feet. So what we need to do is do this from 0 to 8, empty. Oh, sorry, thinking backwards. The tank is 10 feet deep. It wants to know not how much work does it take to get it from 8 to 10, but how much did it take to get it from empty up to 8. So 0 to 8. And then our function would be 57 pi over 4 y squared 10 minus y dy. And then this goes in your calculator. So 57 pi over 4 times x squared 10 minus x. Remember, calculator doesn't care what variable you use. From 0 to 8. So it takes 30,561 joules, or not joules, because we don't have that, we have foot-pounds. Or in the English system. To fill the tank from empty all the way up. All right, sample 4. At 1 p.m., January 1st, 1919, a 90-foot high, 90-foot diameter cylindrical metal tank with Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston's North End exploded. Molasses flooded the streets 30 feet deep, trapping pedestrians and horses, knocking down buildings, oozing into homes. It was eventually tracked all over town and even made its way to the suburbs via trolley cars and people's shoes. It took weeks to clean up. Given that the tank was full of molasses weighing 100 pounds per cubic foot, what was the total force exerted by the molasses on the bottom of the tank at the time it ruptured? So, let's see here. The bottom of the tank, pressure is given by the weight times the height, or the density, should be a better thing. So 100 pounds per cubic foot times the 90 feet, because all the olive oil is above it, so we just need the depth. The pressure is, this is pressure, 9,000 pounds per square foot, so that's the pressure. So if I take this and multiply it by the area of the base, which I can figure out, it is 90 foot. So the area is pi times 45 squared. So if I take my pressure on the bottom times the area, that'll give me the amount of force exerted on the bottom of that tank. So 9,000 times pi times 45 squared is a very, very, very large number. 57255 pounds. The force exerted on the bottom of the tank. What's the total force against the bottom foot-wide band of the tank? Okay. So let's see here. So the force is going to be the pressure times the area. So what you're essentially looking at is, if you got your cylindrical tank, you've got the little bottom foot here. So the area of that band is 2 times pi times r times the change in the depth. 2 pi r gives you the distance around. It's the circumference of that circle that makes up the bottom. The delta y gives you the height of it. So, but we know r is 45, so this is 90 pi delta y. So that's the area. So the force is going to be the pressure, which we found was 9,000. Oh, no, sorry. It's 100 times the depth. Here it was 100 times the full depth. So it's going to be, so this is my area. My pressure is going to be 100 times y. That's how deep that is. So let's see here. So the force is equal to 9,000 pi y delta y. And since we're talking about the bottom 1 foot, the depth is 89 to 90 of 9,000 pi y dy. It's not 0 to 1 because you're measuring depth, so distance down. So the top layer is 89 feet deep. The bottom is 90 feet deep. So 99,000, sorry, pi x from 89 to 90. So let's see here. Total force was 2530552 pounds. So 2,530,552 pounds of force against that bottom wall trying to rupture the tank. All right, so we can also use this in probability issues. So the normal probability function, probability density function is function f of x with domain all real such that the function is always positive, or sorry, not negative for all x, and that the antiderivative include all possible values is 1. Which makes sense because if you think about in terms of probability, if you include all possible outcomes, one of them has to occur. So there's a 100% guarantee that something happens. The probability associated with the interval a to b is just given by the bounds. So find the probability that clock stop between 2 and 5. So let's see here. So probably that you're in any given hour is 1/12. So between 2 and 5, 1/12 dx. So this would be 1/12 x from 2 to 5. So that would be 5/12 minus 2/12, which is 3/12, which is 1/4, or 25%. If you look at the clock, that would make sense because between 2 o'clock and 5 o'clock, that is 1/4 of the clock. All right, so normal probability density function, the normal probability Gaussian curve gives you this outrageous equation. Standard deviation is sigma. X is a specific value. Mu is the mean of the function. You also have this lovely rule down here. 68% of the area will lie within 1 standard deviation, so that means below and above. So mu plus or minus sigma within 2 standard deviations. You have 95%, and within 3 standard deviations, you have 99.7%. Okay, so example 6 says, suppose frozen spinach boxes marked as 10 ounces of spinach have a mean weight of 10.3 ounces, so there's our mu, and a standard deviation of 0.2. Assume that the weights of the spinach boxes are normally distributed. So, what percent of all such spinach boxes can be expected between weigh 10 and 11 ounces? Okay, so we need to write our probability density function. So I need, whoops, shouldn't have got rid of that page. Okay, so let's fill our numbers in. So the probability density function is given by 1 over sigma, so 0.2 square root 2 pi e to the negative quantity x minus 0.2 squared divided by, nope, that's mu, that's 10.3, divided by 2 times 0.2 squared. So that's our function. So between 10 and 11 ounces would be due from 10 to 11 of my function, which the calculator would be a much better way to do this. So 1 over 0.2 square root 2 pi e, whoops, e to the negative quantity x minus 10.3 closed quantity divided by open 2 times 0.2 squared close, from 10 to 11. So you do all that math and you get, oops, shoot, lost a squared. Should be squared right there. Squared. There we go. So this comes out to be 0.933. So there's a 93.3% chance that the weigh between 10 and 11 ounces. What percent would we expect less than 10 ounces? So let's see here. So that would be 0 to 10 of f of x. So I'm just going to go to my previous line and change the bounds, because that's the easier way to do it. If I can get there in a relatively. So from 0 to 10. This comes out to be 0.067, so about 6.7%. All right, exactly 10 ounces. Okay, this is a bit of a trick question. It would be this, and this is always 0. If your bounds are identical, it's 0. But the reason it ends up being 0 mathematically is that the likelihood of getting one exact value out of an infinite distribution of them is 0. There's an infinite number of possible weights. The likelihood of getting one exact weight is essentially 0, because you're dividing 1 out of infinity. Even though technically, there probably are boxes that weigh exactly 10 ounces. All right, and that brings us to the end of the section.